You've probably seen an X-ray before, right? Maybe you've even had one taken of a broken bone. But have you ever stopped to think about the physics behind it? It turns out it's this really cool story about particles, powerful fields, and a very, very sudden stop.
I mean, it all comes down to this one question, really. How on earth do we create something that can blast right through skin and muscle, but get stopped by bone? Well, the answer starts with a process that has this incredible German name.
The secret is something called breaking radiation, and believe me, that name is way more literal than you might think.
The word is Bremsstrahlung. Bremsen means breaking, and Strahlung means radiation. You gotta love how literal that is. It's a perfect name for exactly what's happening at the subatomic level.
So imagine you're in a speeding car and you just slam on the brakes. All that forward energy, that kinetic energy, has to go somewhere, right? It turns into screeching tires and a whole lot of heat. Well, in the quantum world, when a tiny electron moving at incredible speeds slams on the brakes, that lost energy is released in a much, much more interesting way.
So, okay, how does this sudden breaking actually create an X-ray? Well, the magic is all in the physics of that swerve. Okay, so what we're looking at here, these diagrams are basically blueprints for this little interaction. You've got the electron, that straight line, just zipping along, but then it gets deflected by the nucleus. As it swerves, it has to get rid of some energy, and it does that by spitting out a photon, that's the little squiggly line. And that photon, that is our X-ray.
You can really think of it as a simple three-step dance. First, a super-fast electron gets really close to an atomic nucleus. Second, the massive positive charge of that nucleus basically grabs the negatively charged electron and yanks it off its path. And third, that sudden, violent change in direction and speed forces the electron to shed its extra kinetic energy. And it does that by releasing a photon, our X-ray.
All right, so that's the theory. But how do we actually harness this whole process to take a picture of your bones? Let's, metaphorically crack open a standard X-ray machine and see what's going on inside.
So inside the machine, it's a pretty straightforward four-step deal. First, we heat up a little tungsten filament until it literally starts to boil off a cloud of electrons. Then, we use a huge voltage difference to fire these electrons like tiny bullets across a vacuum. And finally, when they smash into the tungsten target at the other end, they stop so violently that they release all that energy as a shower of Bremsstrahlung X-rays.
But here's the crazy part. The whole process is incredibly inefficient. Just look at this. A whopping 99% of the energy from those electrons crashing into the target is just wasted as heat. Only a tiny, tiny 1% actually becomes the useful X-ray photons we need. And that, right there, is why keeping X-ray tubes cool is one of the biggest engineering challenges.
Now, to be fair, Bremsstrahlung isn't the only game in town inside that tube. There's another process going on called characteristic radiation. That happens when one of our bullet electrons actually knocks another electron out of its orbit. But for what we're talking about, Bremsstrahlung is the star of the show. It's responsible for about 80% of the X-ray beam, and it gives us that nice broad range of energies that we need to get a really clear image.
Okay, so far we've only talked about electrons breaking near a nucleus. But what if there is no nucleus? This is where the story gets a really interesting wrinkle, especially when you start looking at things like giant particle accelerators.
And this is a fantastic question that someone asked. In a particle accelerator, a synchrotron, you've got a beam of electrons in a near-perfect vacuum. I mean, there are no nuclei for them to hit. So how in the world is any radiation being produced?
And here it is. This is the big aha moment. It turns out the key isn't the physical lump of protons and neutrons that is the nucleus. The key is the powerful electromagnetic field that the nucleus creates. Anything that can generate a strong enough field to bend the path of an electron is going to make it radiate energy.
And that's exactly what happens in a synchrotron. Instead of a nucleus, scientists use incredibly powerful magnets to steer the electron beam around a circle. Every single time those magnets force the electrons to curve, they are changing direction, they are accelerating, or decelerating, depending on how you look at it. And just like before, that change forces them to release energy as radiation. We call it synchrotron radiation, but really, it's just Bremsstrahlung on a cosmic scale.
So you see, this isn't just some neat trick we use in a hospital or a physics lab. This fundamental process of breaking radiation is happening all across the universe, and its applications are mind-bogglingly diverse.
I mean, just think about the sheer range of this. In medicine, we use it for everything from diagnosing a broken arm to fighting cancer. In industry, it lets us look inside solid steel to check for tiny flaws in a weld. And in astrophysics, astronomers study the breaking radiation from superheated gas to figure out what's going on in the chaotic environments around stars and black holes.
I think this quote just sums it all up perfectly. The simple act of a charged particle changing its path, it leaves behind a trail of light. It's a signature that lets us see things that would otherwise be completely hidden, from a hairline fracture in your bone to the insane dance of plasma around a distant star.
So in the end, breaking radiation is a signature. It's a message broadcast by the universe's most fundamental processes, just waiting for us to figure out how to read it. It gave us a window into our own bodies and into deep space. It kind of makes you wonder, doesn't it? What other invisible phenomena are all around us, just waiting to be seen?